In our last example, I really like this one because it is very geometric in nature. So what we're doing is we're taking a 10-meter long piece of wire and we're cutting it at some place. Okay, and we're making one into a square and one into a equilateral triangle. Okay, so if we call this x, this would be 10 minus x, right? And maybe it actually doesn't matter which one you make into which. The math will work out in the end. I am going to, for simplicity, going to make the piece with x into the equilateral triangle. So each side is x over 3. And then in the square, I'm just going to make sure that there's no confusion that we have a square and an equilateral triangle, but each side would be 10 minus x over 4 in the square. Okay, and now we want to know how should the wire be cut so that the total area enclosed is maximum. Okay, well, area in total, right, if we think of it as a function of x, the square is actually rather easy to compute. The area for that is going to be 10 minus x over 4 all squared. Area of a triangle, side squared. Okay, now for the equilateral triangle, you might need to do a little bit more work, unearth your geometry textbooks, but if you remember, if you make an altitude here, this would be a 30, 60, 90, so then half of the base is x over 6, and then the altitude here would be x over 6 times square root of 3. So I'm just going to do that, x squared 3 over 6. Okay, so then that makes the area of that equilateral triangle 1/2 times the base, which is x over 3, times the height, x square root of 3, all over 6. Okay, there are other variations of that same formula that you could use. That was just the easiest one for me. Okay, but now I've drawn a diagram, identified the constraint, which is this splitting, and then I have an equation. Okay, in terms of x, right, if I think about a domain for x, I should check the endpoints, but again, x can't be 10, nor can it be 0, because if I cut at either one of those, I don't have any figures. I just have a whole wire, or either have a whole square or I have a whole equilateral triangle, but not both. Okay, so it would be easiest if I expanded this and worked with this a little bit. With this first one, if I simplify this, I would get x squared minus 20x plus 100 all over 4, and then this next piece is going to be plus square root of 3 over 36 times x squared. Okay, so then that makes my derivative even easier to compute, so I can find the critical numbers, but I'd end up with x over 2 minus 5x, minus 5, I'm sorry, and then plus square root of 3 over 18x, okay, and set this equal to 0. All right, and so here, once you set or solve for x, you get 5 over 1/2 plus square root of 3 over 18, which is approximately 8.38. Okay, so for this one, you could, if you wanted to verify that this is a maximum, right, you could do the second derivative test, right? So a double prime of x, and you end up with, what, 1/2 plus square root of 3 over 18, which is greater than 0, so that's a local minimum. So we have a local min at x is equal to, or x is approximately 8.38. So then this begs the question, okay, how in the world do we get a maximum, right? This doesn't make sense. So, well, this is one instance where the extreme value, or the maxima is not at the critical point, right? You should be technically checking the endpoints for x too. There aren't endpoints, so so even though in terms of the area, we don't have, so in terms of x, I should say, in terms of x, we don't have 0 and 10, right? Technically, physically, we can allow x to be equal to it, but that just means that in this case that if we allowed x to be 0 or 10, we would either have only a square or only a rectangle or only an equilateral triangle. And if we think about this in context, that could be okay. So where should we cut? And the answer is we don't. So if we look at x and a of t, right, we would technically need to check 0, our critical point of 8.38, and 10, and see what we get. Okay. If we did 0, then what do we get? 100 or 10 over 4, so 2/5, and square that, so 6.25. Okay, and we can complete the rest of the table too. There's the rest of the table filled out. So then, based on this, we can say if we were allowed not to cut, which is the correct answer in this case. So the answer is do not make any cuts, because if we do not cut, then we should take the entire wire and just make a square. Okay, because we do get the maximal area occurring when we have a square instead of trying an intermediate cut or cutting or using the whole thing for a triangle. Okay, so here we go. So the how should the wire be cut? So the answer is do not cut it, but make it into a square. Okay, so this is the only example that we've seen so far where we've had to consider the endpoints. And so know that that's okay to do, but you might have to think carefully within the context to make sure it's okay to consider those endpoints.